A million miles from Earth, the James Webb Space Telescope is observing the universe in a way that goes far beyond simple imaging. It is detecting extremely distant light that has traveled for billions of years, meaning it is essentially seeing the universe's earliest stages. But what it is revealing is not what scientists originally expected. Instead of a slow and gradual formation of structure after the Big Bang, the early universe appears surprisingly active and developed. According to long-standing models, the first stage of cosmic evolution should have been simple, mostly hydrogen and helium spread out in a smooth expansion, with tiny fluctuations gradually growing under gravity. Over long periods, dark matter was expected to gather first, forming invisible scaffolding, and only then would gas fall into these regions, cool down, and begin forming the first stars and galaxies. Early galaxies, under this view, should have been small, faint, and still in the process of assembling. However, observations from the James Webb Space Telescope suggest something very different. It is finding galaxies that look unusually large, bright, and structured at times when the universe was still extremely young, within just a few 100 million years after the Big Bang. Some of these systems appear comparable in size to modern galaxies, containing vast numbers of stars far earlier than expected. This challenges the idea of a slow buildup and suggests a much faster development of cosmic structures. The problem is not just the size of these galaxies but the speed at which they seem to have formed. Galaxy formation is a complex process that normally requires multiple stages: the collapse of dark matter, the inflow of gas, cooling, star formation, and repeated generations of stellar evolution that enrich the galaxy with heavier elements. Each step takes significant time. Yet many early galaxies appear to have completed much of this process far sooner than current theories allow. Initially, scientists considered possible errors or alternative explanations. Some of the apparent mass could be exaggerated by gravitational lensing, where light is magnified by massive objects between us and the distant galaxies. In other cases, bright active black holes at the centers of galaxies may make them look more massive than they truly are. Adjustments to measurements have reduced some of these tensions, but not eliminated them. Even after corrections, there are still more mature and massive galaxies in the early universe than expected. Another major surprise comes from the discovery of supermassive black holes at very early cosmic times. In standard theory, black holes form from collapsing stars and grow slowly by merging and absorbing surrounding matter. There is also a physical limit to how fast they can grow due to radiation pressure pushing incoming material away. Even with efficient growth, reaching billions of solar masses should take a long time. Yet some black holes appear to have reached enormous sizes less than 500 million years after the universe began. This creates a serious gap between observation and theory, suggesting either faster growth mechanisms or the possibility that some black holes began with much larger initial masses than previously thought. Alongside galaxies and black holes, large-scale cosmic structures also appear to have formed earlier than expected. Vast networks of galaxies arranged in filament-like patterns are already visible in the young universe. These structures, which resemble the cosmic web seen today, were thought to require billions of years to fully develop under the influence of gravity. Yet evidence suggests that these large-scale patterns were already emerging surprisingly early. Some regions even show galaxies that formed quickly, evolved rapidly, and then stopped producing new stars sooner than anticipated. Taken together, these observations point to a consistent pattern. The early universe may have developed structure, mass, and complexity much faster than current cosmological models predict. One possibility is that the physics governing the early universe is more efficient than current models assume. Star formation, for example, may have occurred under conditions that allowed gas clouds to collapse faster, producing massive stars in shorter time spans. If early gas was denser or cooled more efficiently than expected, then galaxies could have formed earlier and grown faster than standard timelines predict. Another possibility is that the role of dark matter is not fully understood. Dark matter is thought to provide the gravitational framework that guides galaxy formation, but if its behavior in the early universe differed in subtle ways, it could have accelerated the assembly of large structures. Even small changes in how dark matter interacts with itself or normal matter could significantly alter the pace of cosmic evolution. There is also the question of whether the first generation of stars was more extreme than previously believed. If early stars were significantly more massive than modern ones, they would have burned brighter and lived shorter lives, rapidly enriching their surroundings with heavy elements. This would allow later generations of stars and galaxies to form much faster, compressing what was once thought to be a long timeline into a much shorter one. The early appearance of supermassive black holes adds another layer of complexity. If some black holes formed directly from collapsing gas clouds without first becoming stars, they could bypass traditional growth limits. These so-called direct collapse scenarios would allow black holes to start large and grow quickly, explaining their presence in the young universe. However, the exact conditions required for such processes are still uncertain and difficult to confirm with current observations. Despite these possibilities, no single explanation fully resolves all the tensions. Each adjustment solves part of the puzzle but leaves other pieces unresolved. This is why the current situation in cosmology is not considered a failure of theory, but rather a sign that the picture is incomplete. As more deep field observations are collected, patterns are becoming clearer. The early universe is not just filled with isolated surprises. It consistently shows signs of maturity, structure, and complexity emerging earlier than expected. This repetition across different regions and surveys makes it harder to dismiss the findings as measurement errors or isolated anomalies. In response, researchers are beginning to re-examine some of the fundamental assumptions behind cosmic evolution. The timeline of structure formation, the efficiency of star birth, and the growth rates of black holes are all under renewed scrutiny. Even small revisions in these areas could significantly reshape our understanding of how quickly the universe transitioned from simplicity to complexity. What makes this moment particularly important is that it represents a shift from confirmation to revision. For decades, cosmology has largely refined an already established framework. Now, however, new data is pushing that framework to its limits, suggesting that the early universe may require new physics or at least a deeper understanding of known physics under extreme conditions. In the end, the universe being observed by the James Webb Space Telescope is not contradicting science, but expanding its boundaries. It is revealing that the earliest chapters of cosmic history may have been far more active, efficient, and structurally advanced than anyone previously imagined.